Let us now look again at the compatible intervals problem. As a reminder, the input, we are given a set of n intervals where every interval is given by AI and BI. Again, let's refer them as to start and finish time of a job, just for easier talking. It's easier to talk about them like that. So job AI is given by the start time AI and the finish time BI. AI and BI are real numbers. AI is smaller than BI. A job finishes after it starts. And we are interested in the largest number of intervals from this set A, such that no two of them are overlapping. Again, overlapping, just visualize it on the real line. If you draw to the two intervals, they should not overlap. They should not intersect, okay? So if AI, BI, or A1, B1, and A2, B2 are on the real line, the B1 should be smaller than A2, okay? Or the B2 should be smaller than A1. This is what it means for them to be compatible. So for this problem, we talked about several greedy algorithms. So one of them was, let us sort them by a non-decreasing order of their start times. Okay, so let's sort the n jobs by non-decreasing order of their start times, or the AIs. Okay, so this is an n log n algorithm because we can do merge sort on them. And then let's scan that sorted list and choose first A1, B1, and then jump to the second one. If it's conflicting, we don't choose it and we go to A3, B3, and so on. If it's not conflicting, we can take it. As I said, if greedy algorithm choose by earliest start time. Okay. So the first one is choose by earliest start time. This one we said doesn't work. And we need to come up with a counter example for that. So now when you think about counter example, you need to think about if I choose the one based on the earliest start time, think of an example where when you think about earliest start time, so imagine that this is now the one that's going to have the earliest start time. Think about it that I will create a case where choosing this and getting stuck with this is forcing me not to select many other intervals just because they overlap with it. In other words, think about coming up with a counterexample by creating an instance where choosing that interval with the earliest start time will force you to ignore so many other jobs just because this one overlaps with them. As you can see here, the way I drew it, I made that interval to be very, very long so that it covers so many other intervals. Now, if I have this one here, based on the earliest start time, I will choose this interval here. Once I choose this, I am done. I'm stuck because I cannot choose this. I cannot choose this. I cannot choose this. I cannot choose this. These intervals all overlap. Okay. Now we know that an optimal solution would have been, no, let me choose this and let me choose this and this and this, but not choose this one. Because this solution allows me to schedule 4 jobs instead of 1 that the greedy algorithm would have given. Okay, so choosing by earliest start time doesn't work, and this is a counter example. Again, I'm drawing it here, but you can create the AI and BI values for this based on this drawing. So if you make A1, for example, here, if you make A1 equal 1 and you make B1 equal 100, then you can make A2 equal 3, B2 equal 10, and so on. Okay, so you can now turn this into actual values of these intervals. But this is an example where choosing by the earliest start time, it is a greedy algorithm, it is polynomial time algorithm, but here's a counter example that would have forced the greedy algorithm to tell me just choose 1 job, when I know an optimal solution would have chosen 4 jobs. Okay, so this one doesn't work, as we said. Another one we said doesn't work is basically choose based on the shortest interval. Okay, so choose by the shortest interval. What does this mean? It basically means sort now not based on the start time, but based on the length of every interval. So the length of an interval is bi minus ai. So now this doesn't work either. This doesn't work. And how do we come up with a counterexample? The way to come up with a counterexample, again, since the algorithm is going to choose the shortest interval first, so create an interval here and say this is a short interval, it's going to choose this one. But let it now conflict with many other intervals that we should have chosen. Now, the other intervals, they cannot be shorter than it because the algorithm would have chosen it, okay? So the other intervals need to overlap with it and have to be longer than it. The only thing we can do is actually we can make it overlap with two intervals that are very long, much longer than it. If we have this, so if I say A1 is 10, B1 is 20, and I make A2 equal 1, and B1 equal 15, for example, and let's say A3 equals 16 and B3 equals 100. So if you look at this interval here, this interval is the shortest of all three of them. The algorithm would have chosen it. So the algorithm would have said the maximum number of intervals we can schedule is 1 because we can take A1, B1. However, an optimal solution would have been to choose these two, which are longer than it, because then the solution is here are two intervals that would work, okay? So please keep in mind how we think about coming up with a counterexample. If you want to come up with a counterexample, create an instance where the first element you are choosing is going to create a problem, okay? So in this case here, I created that shortest interval, but if I make it overlap with two other intervals that are longer than it, then this shortest interval basically ruled out the other two intervals, and this already created a problem because I could have chosen two instead of one, okay? And this is very important for you to keep in mind how we think about counterexamples. And another important point to keep in mind that, at least from my experience, I want to share with you is that when I think about a greedy algorithm for a problem like this, and I want to say, is it correct or not correct? Should I prove it? My first reaction is to be very suspicious, okay? So my first reaction to a greedy algorithm is to be suspicious and say, let me try to create a counterexample. And when I start doing that, if I start thinking about a counterexample, I try once, I try twice, 3 times, 4 times, and I keep failing. I cannot come up with a counterexample. That's where I start having stronger belief that maybe the algorithm is actually correct and it works. And that's when I start switching to a mode of let me prove correctness. Okay? This is just my own personal thing. I'm not saying that this is a foolproof technique. But when you give me a greedy algorithm for a problem I've seen for the first time and say, does it work or not? And if it doesn't, give me a counterexample. And if it does, give me a mathematical proof. Unless the problem is intuitive, my first reaction would be, let me actually say that it doesn't work and try to come up with counterexample. If you keep failing coming up with a counterexample, in fact, that failure might start giving you also an idea of how to prove it, okay? How to prove it as well, okay? So we go to the third greedy algorithm, which is choose the intervals by the shortest, by the earliest finish time, by the earliest finish time. Okay. So now the algorithm in this case would be, first step A is sort the jobs or the intervals in non-decreasing order, of BIs, and B, we will basically say that for I equals 1 to n, So we now have them based on the order. So imagine that, actually let me erase this. So imagine that they were sorted as, B1 smaller than B2, smaller than B3, and so on, and smaller than Bn. So this is really the order, that B1 is the smallest, B2 is the second smallest, and so on. Then we go for I equal 1 to n. If, actually, we need to create a list of all these ones here. So, let A, for example, the set of these intervals be the empty set, and C, for I equal 1 to n, if AI, BI is compatible with A, in other words, it's compatible with all the intervals in A, then we add it. Okay, so it's safe now to choose this interval. So A becomes A union this new interval AI, BI. Otherwise, we just ignore, okay? And, D here, basically return A, okay? So this is the algorithm, and if you think about it, if we think about running time, this one here is O of n log n, because we can do merge sort. This is O of 1, and this one here is that how long does it take? Well, it's, if you think about it in the loosest way, you can say, well, every interval we have to compare it with all intervals in the previous one, but we don't need to do that. I mean, if we keep a smart data structure that basically keep for A the largest finish time, and then we can compare AI to the largest finish time in A, because if AI is smaller than one of the finish times, if it's smaller than one of the finish times in A, then this interval is not compatible. I will repeat what I just said. If I want to check if AI is compatible with all the intervals in A, the most naive implementation is to go through every interval in A and compare AI, BI to it to make sure it is compatible. But we don't need to do that. If in the implementation itself, I maintain the largest finish time of all the intervals in A, then how do I check if AI, BI is compatible with A? I just need to check if AI is smaller than that largest finish time. If it is, then it's not compatible. If it's not, then it is compatible and I can move on. So this can be done, the if statement can be done in O of 1 with the right implementation, but we have an entire loop there. It's O of n, and this is O of 1. So we have really an O of n log n algorithm here, okay? So this is a greedy algorithm, and it turns out that this algorithm works, okay? So you should try a few counter examples, and you will see that these counter examples will fail, okay? So now, how do we prove, okay? So we need now to prove, okay? To prove correctness of this algorithm, proof of correctness. And again, I am proving the correctness of the greedy algorithm that chooses by the earliest finish time, okay? By the earliest finish time. Proving correctness of greedy algorithms in general, almost all of them, all the proofs, regardless of the problem, in general, they all have the same strategy, okay? What is the strategy? It's usually a proof by contradiction. You first say, let X be the solution returned by the greedy algorithm. The greedy algorithm that we are trying to prove its correctness, let X be the solution from that greedy algorithm. And since we are trying to prove by contradiction, we say let Y be an optimal solution that's better than X. Okay, let Y be an optimal solution that's better than X. And then we proceed to modify Y to make it exactly like X, and showing that we don't lose the optimality. Okay, so I repeat, you first say let X be the solution returned by the greedy algorithm, and since we are trying to prove by contradiction, it means that there is a solution Y that's more optimal than X, and then we proceed to fix y or change y so that it becomes like x. And by doing that, we have shown that that optimal solution y that you gave me, I could actually turn it into x without losing the optimality value, which is the contradiction. In other words, that y that you give me cannot be more optimal than x. Let us illustrate that proof on this very problem here. Okay, so let's assume, again, I need to do proof by contradiction here. So the proof is by contradiction. Okay, so let's assume, which basically means assume the algorithm we just gave here, which is again sort by in non-decreasing order of finish times and choose based on that order. Assume the algorithm is not optimal. And let A be a solution returned by the algorithm. Okay, so this would be A is the set of intervals that were returned by the algorithm. And now, since I'm trying, by contradiction, we are claiming it is not optimal. It means let B be a set of non-overlapping intervals such that the size of B is smaller than greater than the size of A. Okay, so let's pause for a second. What did I say here? I want to prove that this algorithm is correct, and I want to prove it by contradiction. Which means that let me assume the algorithm is not optimal. Okay, what does that mean? Let me look at the solution returned by the algorithm. This is A. So A is a set of intervals that the algorithm returned. Since I am assuming it is not optimal, it means there is another set of intervals, B, where the intervals on B, again, they are subset of the intervals in the input, are non-overlapping, and the number of intervals in B is larger than the number of intervals in A. So this basically, what we just wrote here is that the algorithm is not optimal, because if the algorithm is optimal, it should have returned B, not A. Okay? So now we need to proceed to show that such a B does not exist. And that basically is what the contradiction is. Okay, so how do we do that? And again, this is one of the other general elements of proving correctness of greedy algorithms. So this algorithm, if you look at A and you look at B, so A is going to be a set of intervals, right? So this is an interval 1, interval 2, interval 3, and I'm listing them. Really, this is, the first interval, the second, the third that were returned by the algorithm. Okay, so this is how the intervals would be. Okay, so imagine that this is the set of intervals that were returned by the algorithms. Okay, so let's call them, this is interval 1, interval 2, 3, 4, 5, and so on. Okay, B is also another set of intervals. Okay, so B is another set of intervals. Something like that. Okay, let me actually, I want to illustrate something here. Okay, so the way we look at it, so the algorithm built the set of intervals as I1, I2, I3, I4, and so on. Let's call the other intervals, this is I, let's call them J1, J2, J3, J4, J5, and so on. And now we do the following. Let's look at I1 versus J1, I2 versus J2, and let us get to the first interval. Let us get to the first interval on which A and B disagree. Okay, so if I1 equals J1, if I1 equals J1, then they agree on this. Okay, so they both have the same interval. If I2 equals J2, they are both have the same interval. I3 equals J3, I4 equals J4. I5 does not equal J5. Okay, so they don't. So 5, the index 5, is the first interval the first interval at which the two solutions disagree, right? So A is a set of intervals, B is a set of intervals. They are sorted. Both of them are sorted by their in non-decreasing order of their finish time. Since B does not equal A, it means that there are at least one interval in which they disagree. Let me focus on the very first interval they disagree on. And for sure, the finish time of J5 is larger than the finish time of I5. For sure, the finish time of J5 is larger than the finish time of J5. Okay? Now, for sure, the finish time of J5 is larger than the finish time of I5, because if it wasn't larger, the algorithm would have chosen J5 then. Okay? So we know that the finish time of J5 is larger than I5. So let me now do the following. Let me remove from B this J5 and add to B this I5. Okay? Now, I know that I5 is compatible with I1 through I4. And since J1 all the way to J4 are compatible, then I5 is also compatible with J1 to J4. So if I look at this, then if I replace J5 by I5, then I have now a set of intervals that are still compatible. So B is still of compatible intervals. And I haven't changed the size of B, right? I haven't changed the size of B. I removed J5 from it. I added I5 to it. And do you see what's happening now? So now we said that the fifth interval was the interval at which A and B disagree. But since it was the first one that it disagrees, now I replaced J5 by I5. So what happened now is that if you look at B, so now B is really, it's I1, I2, because again, J1 equals to I1, J2 equals to I2, and J3 is equal to I3, J4 is equal to I4, and now after I fixed it, J5 is equal to I5. After that, it becomes J6 and so on, right? Now, if they disagree on J6, which means I6 is different from J6, I repeat the same exercise. If they don't, I go to I7 and J7. So I can repeat the same exercise here, and what am I doing? I'm transforming B into A without violating the overlapping property. So I'm transforming B to A by replacing JK by IK, without affecting, again, the overlap property, and without reducing the size of B. So after this exercise, if I repeat this, then I have transformed B into A, and B now is the same size as the original B, and B equals A, right? Which is the contradiction, in the sense that I kept replacing things in B by their counterparts in A without reducing the size of B, which means the size of B equals the size of A to begin with. And this finishes the proof. Okay? So to summarize again how I went about establishing the proof is I assume the algorithm is not optimal. I say let A be a solution that's coming from the algorithm. Since it's not optimal, there's another solution B that is, in this case, since we are looking for a maximum solution, maximum length, let's assume there is a B that is larger than A. I basically align A and B. I say, let me look at them both at the same time, and let me go through the intervals in both of them one by one. As long as the intervals in both of them are the same, I keep going to the next interval. Then I got to interval 5, and I noticed, okay, A and B disagree on interval 5. And then I argued that if you replace interval J5 by interval I5, you did not create a conflict, and you did not reduce the size of B, so it's a safe choice. It's a safe replacement. And then I continue doing that. I go to the 6th interval, 7th interval, and I keep replacing things in B that differ from A. At the end of this exercise, I have gotten to B equal A in terms of size and in terms of content. And this is where the contradiction is. Therefore, the algorithm is optimal.